Hello everyone, the first speaker is 郑慧文. Let's welcome her.
Okay. Hi everyone, my name is Hui Zhen and this is my paper. And today I will introduce this paper. And the topic is in vivo investigation of foreign nanodrugs for treating triple negative breast cancer. They are for neutral capture therapy. And this paper is from biomaterial evidence. And the impact factor is 5.5. The ranking is Q2 from biomaterials. And this is my outline. And my first, I will have a short talk about this study's results and the conclusion. And then I will introduce this study. And this study is divided into three parts. And the first part is in vitro study. And it will talk about the preparation and the presentation of the PG code BCMO, and which is the nanodrug compound in this study. And the second part is cell study. And it will use cytotoxicity assay, follow uptake, and the effect of NCT on breast cancer cells. And the third part is animal study. And it will discuss about the biodistribution and the effects and the safety of PG called BCNO and at the end have a assumption of this study. And this purpose is of this study is to demonstrate that PG called BCNO on BNCT is more potential than the clinical drug of BPA in the treatment of triple negative breast cancer. And the results proves that PG code BCMO inhibited the greatest delay in the tumor growth time for 9 days. And compared to treatment with BPA, and it also demonstrated that the PG code BCMO treated mice had extensive tumor autopsy and lower probability of cancer recurrence. And before this study, we have to know about breast cancer first. And breast cancer affects 30% of women globally. And it also the second most common type of cancer among the female. And it can be classified into number A or B. And HER2 and the triple negative breast cancer is also called TNBC, and it based on the pathological parameters in immune histochemistry, and such as the presence of hormone receptor HER2 and the proliferation index like Ki67. And in this type, five types of cancer cells, triple negative present triple negative breast cancer is recognized as a highly proliferation cancer cell because it's without the ER and the EGFR receptor. So that it's difficult to do some treatment such as chemotherapy or radiation therapy. And so this study choose this kind of cell lines to discuss it. And recently, research suggests that oral neutral capture therapy, and also called BNCT, may be an effective treatment for locally advanced or TNBC patients. And this study also chose a BNCT to observe the effect on TNBC by using the nanodrug. And BNCT is the interaction of thermal neutrons and boron 10. And when the boron neutron hits the boron 10, it will release helium 7 and high energy gamma particles. And these high LET particles can selectively destroy the tumor cells. And because the short RNA is instead of the alpha particle, the normal cells are not destroyed at all. However, the major failure of BNCT is the cancer recurrence. And one of the reasons for recurrence after BNCT is the insufficient and non-homogeneous uptake of the bone just within the neuron. And now there is only two FDA approved oral drugs for VNCT. One is for BSH and the other is BPA. And however, neither of these drugs hardly fulfill the requirement for successful VNCT, and such as BSH is a large molecule and it's not easy to go through the blood-brain barrier. And BPA relies on the AT1 transporter and for intercellular delivery. And it's only suitable for those cancer cells that overexpress the AT1 receptor. And BPA is also easily pumped out by the LT1 receptor upon the cellular internalization. And to improve the quality of bone drug accumulation, and most researchers are focused on the development of third generation bone agent with different strategy, and such as liposomes, antibody, and bone-based nanodrugs in this study. And PG code BCNO is a nanoparticle which was used in this study. It was combined with carbon boron and nitrogen salts. And then the coated PEG to reduce the cytotoxicity and enhance their circulation time in the blood. And the size of PEG code BCNO is about 134 nanometers. This size can enter the cancer cell through the enhanced permeability retention effect and called EPR effect. And this process will cause a vascular endothelial cells to create the gaps. And that can let the cancer cell get more nutrient and oxygen. Through this process, for more PG called BCNO can enter the tumor cells. And choose the best concentration of nanodrug. The viability of cells treated with the bare BCNO, PG called BCNO, and EPA by using the NTS assay. And the cells were treated from 0 to 1000 micrograms per millimeter for 24 and 48 and 72 hours. Then the cell viability was calculated with this formula. And you can see that the IC10 of bare BCNO is 31 microgram per millimeter, and PG called BCNO is 125 microgram per millimeter, and BPA is 500 microgram per millimeter. So based on this result, the intracellular bone uptake was evaluated by incubating a breast cancer cell in 125 microgram per milliliter for 6 and 12 hours. And the bone concentration in the cell was measured by the ICD max. And in the figure, both bare BCNO and PG called BCNO inhibited a high intracellular bone uptake about 60 nanograms per 1000 cells at 6 hours, and 70 nanograms per 1000 cells at 12 hours. And this result indicated that BCNO nanodrug is higher bone loading than BPA in the cells. And we can know that PG called BCNO is the potent normal number drug for BNCT. And for studying the cellular internalization, the author extend the cells with diode and DAPI to recognize the cell membranes and nucleus, and it will appear red and blue respectively under the microscope. And these confocal microscopic results are consistent in the oral uptake results, which is measured by the ICP mass. And for PG code BCMO shows a higher cellular uptake and the narrow particle increase with the oral incubation time. And to know the effect of BNCT on the cancer cell with nanodrug, the cell wall irradiation with the thermal neutral for 45 minutes. After the irradiation, the figure shows that TMPC cells treated with BCNO and PG-code BCNO demonstrate a significant reduction in the cell viability compared to the BPA treatment. And through this result, we can continue to do the animal study. And before doing the BNCT therapy, we have to know the in vivo biodistribution of the oral drug to determine the effectiveness for BNCT and the dose of each drug at 20 milligrams per kilometer were injected intravenously into the tumor-bearing mice with breast cancer cells on the day 1 and day 3. And to maximize the drug delivery efficiency, then the mice were euthanized in 24 hours and the amount of tumor, blood, and major organs were measured by the ICP mass. So as you can see that nanoparticle in liver, spleen, and lung will achieve a higher phonogen loading, and that's because macrophages are prefer to uptake the nanoparticle. Although the phonogen in tumor is not very much, the TB ratio is about 3.5, and which is suitable for effective BNCT without harmful side effects. And this finding suggests that PG code BCNO in BNCT is potential for targeting TNBC cells. And in the in vivo BNCT treatment of mice bearing MDA and B231, the mice were divided into 3 groups. One is control group and EAPA group and PG-CoBC group. And the tumor growth were monitored by them for 35 days after the radiation. And this formula is for calculating the tumor size. As the data presents, the lower of the value means the smaller of the tumor size. So the results show that mice treated with PG or BCNO had a significant delay in the tumor growth for 9 days, compared to the mice treated with BPA over 1 day. And to demonstrate the specificity of BNCT in the cancer cells, the author also monitored the mice body weight for 35 days and found that there is no significant weight loss, and this suggesting that PG-CoBCNO in BNCT offer a higher effective in the and targeting the therapy for minimal side effects. And in addition to monitor the changes in the body weight, there's another way to demonstrate that PG code BCNO is more potential oral drugs that is observed in immunohistochemistry staining of p53 as autophagy. And P53 is kind of tumor superiority, and but the mutation of P53 is overexpressed in the cancer cell, and it will show the ground correlation, and the result in the PG called BCMO indicated that it can inhibit the cancer recurrence. And phase 3 is kind of autogene disease. And in the PG called BCMO group show the extensive ground correlation. It means that there is a high degree of cell apoptosis. And so like we can know that PG code BCMO with BNCC is more effective in curing TNBC compared to the BPA with BNCC. And finally, in order to assess the safety of PG code BCMO now drug, you have to observe the major organ of the mouse. And you can see that the treatment with P-glucose didn't have a significant damage compared to the control group. And this finding indicated that P-glucose drug didn't induce adverse effects in these organs during 35 days of treatment. And in this study, demonstrate that PG code BCMO inhibiting the high hormone pent-up accumulation at the tumor tissue, and the greatest delay in tumor growth time, and had extensive tumor apoptosis and lower probability of cancer recurrence. And summarize this result, PG code BCMO nanoparticles and become natural nanodrug in BNCT triple negative breast cancer. Thank you.
Anyone have any question?
Why did you choose this study was about the BNCT application about BNCT triple negative breast cancer. So this study will let me know about the method in my future.
What is PEG and how can it reduce the toxicity?
What is PEG? I forgot the Chinese. But it can code it on the ground particle, and it will follow it will be the most dense stability on the nanoparticle, so it will not be cleaned out by the bodies. 中文就是它会让你比较稳定，然后它可能不会那么容易被身体代谢掉。It is can actually drug enough to the body.
Same page. I want to ask, can you explain like why people sleep and has higher oxygen tumor?
These organs have more macrophage, and these macrophages can obtain a large more than organs.
Six. In the third generation of drugs, what are the electrical nanoparticles compared to the other two types?
Because nanoparticle can have a more volume and tumor accumulation efficiency, and it is also stability.
Is your research also focused on BNCD treated this kind of tumor?
Okay.
Is your research also focused on BNCD treated this kind of tumor?
Yes.
And will you choose the similar drug like say post PEG on the oral drug? Will you also use this method?
I will not use this kind of knowledge, and but I have there's I continue the study from Xu so Xu Jie 合成一个 oral drug, and I will have the cell experience and animal experience. We continue her study.
So in your research, you will do the biological experiments, the reproduction. You and when you do the biological experiments, that's the reproduction.
Yes. Is it? I will use the experiment.
就是你会做这些简报上提到的生物实验、细胞实验或动物实验。
Yes.
那我想问个问题就是我还是一个容易转移的癌症，那你认为使用 BNCT 的这个药物有办法降低它的这个转移发生的几率？
I think it will not very research about this kind of cell. It's triple negative cells. It is not very research about this, but I think there's a lot of research will focus on this because it will have a what the word therapy. So that's
I have some questions. Because you mentioned about they inject the drug and then the drug accumulates in the tumor by EPR effect, right? But actually, EPR effect is not an active targeting, because LAT1 is an active targeting route for EPA, but EPR describes the malfunction of the vascular, which means the vascular will have big holes or high permeability. So the drug, when they inject into the blood vessel, and then the drug will release very quickly. But the release did not mean that the tumor cell uptake the drug. They may be just retained outside of the cell. So actually the paper did not explain the mechanism, how the cells uptake the PEG particle, right?
They only said the particle will get to release.
Yeah, because EPI, that means the vessel is the leakage of the vessel. Yeah, so maybe because they are cells, but they are also the intracell space. So if the drug is delivered based on the EPI effect, the drug will retain on the intracellular space, but not go to the cell. Yeah.
This method didn't get more introduced about this technique.
Yeah. So that's the main issue, because if you develop a new drug and you want to test its treatment efficacy, you have to explain the mechanism. And also in your last picture, you mentioned about the tissue side effect, about the lung and the liver, right? So in the BTA and the PEG group, did they give the neutron irradiation?
Yes.
Okay.
This is a picture after the 35 days of the irradiation.
Okay. Because in your biodistribution measurement, the lung and the liver have very high uptake. So high, there's no side effect.
Oh, in this paper, they use this image and to avoid others normal organs to irradiate.
So you mean that in their irradiation data, actually not the whole mice
Yes.
is covered by the field size. The field size is only open to the tumor site.
Yeah.
So of course there's no damage to the lung and liver.
Yeah.
So if they want to do this study, they have to cover only normal tissue within the field size. So they can actually assay the tissue size. Okay, I just point out the problems of the experiment design. Okay.
Thanks for the presentation.
The next speaker is Bill Honda. Let's welcome him.
Hello everyone, and
my topic is measuring the spatial distribution of the 47 AKB from gamma rays to estimate the long-term region during PNCT treatment. The purpose of the study is providing the treatment to improve the treatment outcome of the patients. So first I will introduce the BNCT. And BNCT is a binary cancer therapy. It combines the thermal neutron irradiation and voluntary injection like BVA and ESH. And this is the flow chart of the BNCT. And in the beginning, patients are injected the voluntary included drug, and it will selectively accumulate in the tumor. After neutron irradiation, the interaction between the neutron and voluntary will produce the listen 7 and the alpha particle, which has high LET and short range, so it can only kill damaged tumor cell, not damage normal tissue. So, however, it is important to verify whether voluntary is deposited in the correct location, like tumor. And so we measure the 47A KB from gamma rays to monitor the distribution of voluntary in the human body during the therapy. And the effect of BNCT is mainly depends on the neutron beam quality and the voluntary distribution in the human body. And many people want to know the voluntary distribution during therapy to evaluate the treatment effect and side effects. And then for measuring the spatial distribution of 47A KB from gamma rays can solve this issue. The from gamma rays are emitted from the excitation of the listen 7. Listen 7 which produced by the boron neutron chemical reaction. And from gamma rays the gamma rays have the specific energy and are produced in real time and making them suitable for the estimation of voluntary distribution during the treatment. So we can measure the 47 AKB from gamma rays to calculate the voluntary distribution in real time. And what is the difficulty of the measurement? And the main difficulty is 511 kV annihilation gamma rays will be produced. And the 511 kV annihilation gamma rays comes from the pair production and the annihilation between the high energy gamma rays and the lead and the collimator, which comprises of lead or target. And the high energy gamma rays are induced by the reaction between the neutron and the hydrogen. The hydrogen is also existed in the human body or the environment. And so the energy of neutron induced from gamma rays and the radiation gamma are too close to discriminate them. So we need to use the advanced data with the high energy resolution, like such as HPG or GTDE or SI2 LBR3 detector. The HPG detector is a semiconductor detector that has high requirements. For the operating environment and is relatively expensive. So this is unsuitable for measuring the operation in the neutron field. And the LIBR detector is a scintillator detector and is relatively cheap and it's not damaged by the neutron particle. And the second difficulty is the relative low yield of the 47 AKB from gamma rays. If the yield of the from gamma rays is lower than then 1/10 of the emission gamma rays, the energy peak of the Planck gamma rays may be covered by emission gamma peak. So we can't analyze the 478 Planck gamma rays energy peak easily. And the method of measuring Planck gamma rays mainly are the common camera and the Planck gamma ray spectroscopy. A common camera can provide 2D or 3D spatial information, which consists of a scatter and an absorber. The principle of common camera is based on the common scattering. And in your analysis, the inclination position of the scatter and the absorber. After multiple scattering, the source of the gamma rays can be determined by the back projection methods. Right figure shows the energy spectrum measured by the common camera, and the image is also shown here. And this is the 478 keV energy peak. And this hotspot is means to the 478 keV means to the it represents the source of the 478 keV part. 478 keV Planck gamma rays. And as the image can provide information of the boron type. However, the common camera is not suitable for detecting low energy gamma rays due to the low precision of the common scattering such as energy, and this is too intensive of the whole system. And the second method is Planck gamma ray spectroscopy. Its method is mainly used to verify the proton range verification. And the experimental design is to measure 4.44 eV Planck gamma rays to confirm the proton range. And this paper used LABX detector with a 2 mm speed collimator to measure the Planck gamma ray spatial distribution. And we will move the phantom. Instead of moving the detection system to measure the specific depth, to measure the Planck gamma rays intensity at specific depths. And after measure multiple depths, we can plot the curve of the photon range and estimate the Planck gamma ray spatial distribution. And the black line is a real photon range, and the other lines show the different AV Planck gamma rays. Shows the spatial distribution of different energy Planck gamma rays, and the figure show the spatial distribution of every energy is similar to the real photon range. So the Planck gamma spectroscopy is an effective method to estimate the primary particle distribution. So I will review the paper to prove the feasibility of estimating the boron distribution by Planck gamma ray spectroscopy in the BNCT. And the paper used the enhanced LABX detector, which coupled into the SIPN semiconductor to measure the distribution of 478 keV Planck gamma rays. And the detector is covered by cadmium foil to prevent the neutron activation and neutron radiation damage. Then they use the pinhole lead collimator with a thickness of 10 centimeter to block unwanted gamma rays through the detector. The accuracy of estimating the distribution of boron is highly depends on the spatial resolution and geometry detection efficiency, which are 8 mm and 3.84 10 powers minus 6 here. And they use the 1000 ppm boron 10 solution as the target. and irradiated the phantom by a thermal neutron with 2 plus 1 million neutron flux. And this figure shows a Planck gamma rays energy spectrum. And this is 478 Planck gamma rays energy peak, and this is 511 keV annihilation gamma. And these two peaks is neutron Kdn temperature variation induced gamma. And the LABR the enhanced LABR detector with 2.5% energy resolution and 62 keV energy peak, but it still can discriminate 478 keV energy peak and 511 keV peak perfectly. But we can use some algorithm to self-train, like the Gaussian unfolding or double Gaussian fitting or detector response deconvolution. So the results show the feasibility of measuring 478 keV Planck gamma rays by Planck gamma rays spectroscopy in the VNCT. And the second part is to be noticed that the neutron-induced noise will degrade the performance of the detector. And the figures show the gamma energy spectrum with and without cadmium foil covered, and which can absorb the thermal neutron to prevent the detector interaction with the neutron. And the blue line is the unshielded detector measured spectrum, and the green line is the shielded detector measured spectrum. And the spectrum shows the cadmium foil can reduce the thermal neutron induced noise because produce cadmium neutron temperature variation induced gamma like 558 keV and 61 keV energy peak. However, this gamma rays energy is much higher than the 47 keV Planck gamma energy peak, and it doesn't affect the analysis. So we also use the Planck gamma rays spectroscopy method to enhance LABR detector, which covered by the cadmium foil to measure the spatial resolution of 478 keV Planck gamma rays. But I use a SLIS collimator instead of a pinhole collimator due to the difficulty of the machine technique. And now we will explain my methods. The experimental purpose is measure the linearity between the boron tank concentration and 478 keV Planck gamma rays intensity. And second is measure the spatial distribution of 478 keV Planck gamma rays to estimate the boron tank region. And the experimental design is shown here. The phantom is placed in front of the beam-pole to 250 millimeter. The detector system was placed perpendicular to the propagation axis of a neutron beam. The detector is composed of the enhanced LABR laser, which coupled to the Hamamatsu 6231 PNT. And the detector is placed in the circle lead shielding to block the gamma noise. And the shielding is also covered by 4 mm thickness cadmium foil to prevent the thermal neutron noise. And in front of the detector, I use the lead to construct the collimator with 1.5 mm slit to filter out unwanted gamma rays. Finally, the signal from the detector is digitized by the 573 SPD detaser and use a compass software to analyze the signal and plot the energy spectrum. And then we use the PNA Fenton and the boron 10 solution to simulate the human tissue and the boron content tumor tissue. The detail of the Fenton structure is shown here. And the Fenton will be moved along the beam pathway to specific depths. And the detection system measure the gamma rays intensity at different depths to get a spatial distribution of gamma rays. And this is the photo of the experiment. And this is a detector, and this is the collimator. The Fenton is here, and the Fenton will move by the moving platform. And this is a beanpole. The beanpole is being covered by the shutter, and the shutter will block the thermal neutron out from the beanpole when doesn't anyone to use the beanpole. And before the measurement, the detector need to be calibrated, including the energy and resolution correction. For the energy correction, I measure the EU152 and the copper 16 and Cerium 137 standard source and fit the photon peak by the Gaussian equation to get a peak center in channel. The energy of photon peak is none because they are the standard source. So we can plot the channel to peak energy transformation curve here. And then also do the linear equation fitting to get the energy correlation parameter. And this function also can, and at the end we can transfer the ADC channel to the energy by this function. And for the energy resolution correction, the purpose of this correction is to get a simulation parameter for estimating the ability of discrete the 478 kV and 511 kV energy peak. So we fit in the 6 energy peak in energy correction already. So we also can calculate the FWHM by the standard deviation of the Gaussian fitting equation. Then it can plot the FWHM to energy curve and fit this curve by power law equation to get alpha, beta, and gamma parameter, which discriminate the process of from radiation to electronic signal, and this we are used in the simulation. And then we do the simulation to evaluate the ability of discriminating the 478 kV and 511 kV energy peak. And this is a simulation model. And we build a 478 kV and 511 kV isotropic gamma source here. And we will emit the gamma rays isotropic. And this is a one inch LABR scintillator, and this scintillator will take the electron or positron deposit energy from the positron or electron, which induced by the 478 kV or 511 kV gamma rays induced. And after retaining the deposit energy in the scintillator, I can plot the deposit energy spectrum, and it will be broadened by the Gaussian experiments algorithm to simulate the process of scintillation light transmission. And the algorithm is shown here. And the alpha, beta, gamma is guessed by the energy resolution correlation. And finally, it can get a Gaussian broad energy spectrum. So here, and as a result, the detector can discriminate the 478 kV and 511 kV energy peak. Not perfect, but we also can celebrated then by the Gaussian folding or detector response deconvolution algorithm to do it. So, and the second part is we need to design we need to choose the design of the collimator. The design of the collimator is important parameter in this study because the collimator will produce too many annihilation gamma rays. So the well-designed collimator can reduce the amount of annihilation gamma rays to. And however, the design should be considered the detection efficiency and the spatial resolution. We simulate a 3-type collimator design, and they are shown in the table. And these have a different thickness slits and a different length. The spatial resolution of a detection system is determined by the collimator length and the slit width. And we aim to design a collimator with the smallest possible bound will achieve a high detection efficiency and acceptable spatial distribution. And as a result, the collimator with 20 centimeter length and 1.5 millimeter width slit is a best choice due to the high detection efficiency and the small margin of lead. And the figure shows the detector response function, which calculated by the simulation, and the spatial resolution of the collimator is about 4 millimeter here. And the study is operated in the W1 port at THOR with 1.4 megawatt rated power, and the thermal neutron flux is about 10 power 6, which defined by the Gulf activation methods. And this figure shows the structure of the THOR, and it has 7 beam ports, and W1 to W3, E1 to E3, and the BNCT ports. The neutron spectrum of the E1 to E3 ports is mainly composed of phase and emitting neutrons, but they are all shut down now. And W1 to W3, the neutron energy spectrum of W1 to W3 are composed of thermal neutron, and W1 is used for the neutron image application, and W2 shutdowns now, and W3 is used to small angle scatter ring application. And this study is measured in the W1. And this is the result, the linearity result. The major gamma energy spectrum with 1000 dPm boron-take concentration is shown here, and this is 478 keV peak, and this is 511 keV energy peak. As a spectrum, the 478 keV and 511 keV peak can be separated by the Gaussian unfolding methods, which means a simple double Gaussian equation to use to fitting. Then I will capture the fitting curve of 7 different boron-take concentration and show here. I show them together as a figure show. We can observe the intensity of the 478 keV from gamma rays intensity is proportional to the boron-take concentration. And this figure shows the linearity between the boron-take concentration and 478 keV from gamma rays intensity. And the linearity is evaluated by the R-square value, and the value is 0.1991 here, which means the high linear relationship between the boron-take concentration and the from gamma rays intensity. And in summary, the detection system is sensitive to the variation of the boron-take concentration, and the detection limit of the concentration is about 30 ppm, and which is also the boron-take including drug accumulated in the tumor in clinical. And the results show the spatial distribution of the 47AK from gamma rays. The spatial distribution is calculated by the peak height analysis methods. The flow of this method is capture the 47AK fitting curve at different depths of the vector. Then get a peak maximum intensity to represent the gamma rays intensity at specific depths. And finally, plot the peak intensity versus the depth curve, and we can get a spatial distribution along the depth, and the distribution is shown here. The blue red and green lines represent the different Bromtand concentration here. And the spatial distribution of 47AK from gamma rays can use to discriminating the initial depth of Bromtand for every Bromtand concentration, but it is hard to discriminate the depth of a Bromtand region due to the soft neutron beam, which the penetration depth of the thermal neutron is too superficial. And the intensity of the 47AK from gamma rays and the Bromtand region, which deeper than 50 mm, is almost equal to the region without Bromtand solution, like PNA or A. And this is the conclusion of this study. And this study have developed a slit calorimeter-based detection system for measuring the spatial distribution of gamma rays to estimating the Bromtand distribution in the human body or in the fetus. And the detection system can discriminate the 47M and the 511K energy peak by Gaussian unfolding method perfect. And the design of calorimeter is important for measuring the 47AK from gamma rays, and this study also evaluates them by the multi-color simulation. And the detection system can be used to confirm the distribution of 250 and 62.5 ppm Bromtand solution in the phantom. And the limit depth of the target is about 50 mm, which depends on the neutron beam energy and the Bromtand concentration. Thank you for your listening.
Does anyone have?
Why would you choose LAVR3 not SRI2 for your experiment?
The decay time of VR2 data is about 300 nanoseconds, and the SRI2 is about 1,600 nanoseconds. But BNCT is operated in the high neutron flux environment. So if we use the SRI2 detector to measure the neutron-induced gamma rays, it maybe can't discriminate the signal and cause to the Pfeiffer effect. And the detection system can analysis the signal， 就是之前系统比较没有办法去 ，LAVR 的 decay time 差不多在300，然后那 SRI 的1600，然后但是如果BNCT是在一个高中总量的情况下去操作，那产生出来的光gamma ray同样是会是在一个很高的光子通量，那这样子的情况下就很有可能导致这个，如果是用 SRI 的这点器的话，可能会导致具有讯号堆积的情形，但讯号堆积 的话，会导致这个能量的辨别是无法去有效去分析的。比如说，它信号对齐的话，代表是它有那个 pulse 在同样的辨识区间内直接被重叠起来。那原本是1AeV 的伽马 rays 会因为重叠而跑到2AeV 的伽马 rays， 所以原本应该要在1AV 的 channel 讯号会跑到2AV 去，那这样子会导致这个讯号整体的失真，所以不选择使用这种长 decay time 的增减器。
So you said that photon gamma ray spectroscopy method is used to verify the photon range in photon therapy, and the paper used to moving the detector. Why you used to moving the paper?
The paper also used moving the detector.
And 那你之后有打算要去移动你的 detector？
就理论上来讲，最理想是要去移动整个增减系统，让这个假体在固定位置上去量测。就用增减器移动不同位置去量测特定的深度的强度的伽马强度，但是因为增值太重，所以通常大家都会选择去移动假体。但是移动假体有一个前提是，这个并的 diverge 不能太大，就是它的发散不能太大，它必须在这个并的传递的路线上的每一个强度都要是相差不多的。但是像是这边的 proton therapy， 因为 proton 是带电粒子，所以它在空气中并不容易，它是会有一个比较高的指向性。但是 neutron 的话，它是一种比较像伽马的一种粒子，所以它是不带电，所以它很容易，它有点像是伽马的 mean free pace， 它会在空间中这样乱弹。对，所以其实我们没有办法去估计这个并的 diverge。所以理想上，在使用这种方法使用在 neutron 的环境下的话，应该是要去移动这个增减器去做第一个步骤是确认这个并它在每一个位置上的强度都是一样的，我们才能去透过移动假体。但是目前的话，我们还是先透过移动假体去做到这件事情，但是有结果的，我们也可以知道说，其实这个 neutron 并目前的 diverge 其实是没有很大的。在高浓度的情况下，可以看到它其实在刚进入波动态的时候就已经有很高的这个光伽马的强度。那如果说这个并不是在每一个深度都是一致的时候，就会像这个低浓度的时候还会有这样子的现象，就是它的强度会慢慢的往上，因为其实越深的深度，它这个假体离冰破的距离是越近，所以说如果它的这个并的强度是随着它走的距离发散的越远，代表它强度会随着渐渐的下降。那在这个 spatial diffusion 上，它是会反过来的，因为要把并到达比较深的深度，是要把分流前是要移往冰头，这你会看到这里有一个斜线上升。那这个斜线上升的情形，我们就认为是这个并的diverge造成的。
Why is the detector signal that's 19 degrees?
The angular distribution of the physical gamma ray is almost 90 degrees. So we place the detector system at a 90 degree to detect more gamma rays due to a low yield of them.
Can you explain about and how did you determine the neutron flux?
This flux is determined by the answer from Italy, and I also determine the neutron flux and the THOR and the W1 pole and THOR. And if you the flux is determined by the neutron activation basis. So这个往中文讲是有点太难，就是它的通量是用极限活化法去量测，但极限活化法也就是氢和中子作用的时候会产生一个412 keV 的伽马，那这个伽马的产量就是氢会被中子活化，那活化的这个活度会和这个中子通量是正比的。那这个所以首先我们要先回推出这个。它中子化去造为中子的时候，那氢要被活化，那我活化之后，我们再使用这个 HPG detector 去量测它的中子能谱。那量测它的中子能谱之后，可以去截取到这个412 keV 的能峰。那这个能峰其实就代表在某种意义上就代表着这个晶线被活化之后的活度。对，那我们可以透过去算这个能峰的 peak， 去截取这个 peak 的total 的 content rate， 然后去除上这个 AU198 它的 detecting 的 bench ratio 和 detection efficiency 就可以得到它的绝对活度。那得到这个晶被活化后的绝对活度之后，可以透过这个算式去得到它的饱和活度。那饱和活度也就是去考虑了它在这个照射完之后拿到 HPG 的时间，还有它在照射时间内的这个活度的 decay， 那考虑这个活度的 decay 得到饱和活度之后，可以再借由这个去考虑这个生物链床和晶作用的 coefficient， 还有晶的重量，去回推出这个生物链床的 flux。对，那主要现在大家在不同的中子场去定义这个生物链床的量，或是 AB 什么的量，最标准方法应该就是这个晶线活化法。对，那晶线活化法它可能有不同的，像是晶箔或是显线都是有可能的。对。
Okay, the next speaker is Yang-Su Li. Let's welcome her. Hello everyone, I'm Yang-Su Li. Today I'm going to present on the topic of a parametric study of computational radiation dose in interventional radiology by Monte Carlo simulations. Its journal is Physica Medica, and its impact factor is 2.685. And its ranking is Q2. Here is my outline, which includes the purpose, conclusion, materials and methods, and results and discussion. The method is divided into 3 parts, and the results are effect of changing these parameters, and independent effect of each parameter's summary. And the last is results of the multiple regression analysis. The purpose is this study is to conduct a parametric investigation using the Monte Carlo simulation method to explore the impact of various factors in interventional radiology on the radiation dose received by operators. The result of random forest regression analysis shows that the primary thin projection has the greatest impact on operator dose. And this study can be used to train interventional radiology staff to improve their procedures and reduce occupational radiation exposure through optimal beam settings. Now I'm going to talk about the materials and methods. X-ray tube use a tungsten target as its anode material, and its angle is 12 degrees, and with a 2.5 millimeter luminance filtration. The study parameters include the tube voltage and beam projection, and FOV and SID, and last is beam quality. This figure shows the typical geometrical setup in interventional radiology. And in this setup, the operator is represented as a RAF Benton. However, in this study, only the dose at the location of the dosimeter was calculated. This figure shows the geometric structure used in MCMP. The patient was modeled as a prism with a length of 100 centimeter and a width of 32 centimeter, and its thickness is 23 centimeter, composed of ICRU tissue. The image intensifier was simulated as a 0.3 centimeter thick lead layer, and the patient's bed and mattress were simulated as a 2.5 millimeter aluminum to account for their equivalent and attenuation. The purpose of this simplification was to optimize the simulation runtime and expand the number of simulations that could be performed. The next is tally and dose calculation. The S6 tally is a tool used to calculate the absorbed dose, approximating the personal dose equivalent HP10. It records the energy deposition of each particle within a region located behind a 10 millimeter tissue equivalent volume. And this region faces the right side of the patient Benton. The tally valve is located at here. This position represents the most common operator location during femoral or radial artery procedures, and aligns with findings from previous studies in the literature. A KAP meter was placed in a thin air layer at 20 centimeters from the radiation source. The size of this layer was scaled according to the X-ray field dimensions to fully cover the beam and rotation along with both the radiation source and the image detector. Since all calculated doses are based on simulated particles, normalization to reference value is required. This reference value is the KAP, which can be measured experimentally and recorded in the radiation dose structure report as defined by DICOM. RDSR is the most commonly used method for recording and storing dose data. The absolute dose in the simulation is expressed as the energy deposition per particle, but this value itself has no direct clinical significance. Therefore, to convert the simulation results into doses under actual radiation fields, it must be multiplied by a scaling factor, which is the ratio. The ratio is calculated based on the KAP, a radiation field parameter that can be measured experimentally. Thus, by applying this ratio, the simulation results can be matched to clinical experiment conditions. The next method is multiple regression analysis. The polynomial multiple regression is a polynomial regression model of degree n for a single variable x. Here the y is the dependent variable, and the beta is the regression coefficients corresponding to different powers of the independent variable x, and the epsilon is the residual error. As the polynomial degree increases, the complexity of the model also increases. Therefore, the value of n must be carefully chosen. If n is too low, the model cannot properly fit the data. If n is too high, it may lead to overfitting. Our model is built using the polynomial regression implement from this scikit-learn, which associates 6 independent variables with the dependent variable y. Polynomial regression is a two-step process. First, the data is transformed into a polynomial using scikit-learn's polynomial features function. Then linear regression is used to fit the parameters. To determine the optimal degree that produces the highest accuracy, root mean squared error is one of the most widely used evaluation metrics in polynomial regression problems. It is calculated by taking the difference between the model's predicted values and the actual values, then dividing by n and taking the square root. They tested polynomial degrees up to the 10th power and concluded that the RMSE was minimized at the third degree polynomial, indicating the best model accuracy. And the random forest regression is one of the most popular machine learning methods due to its relatively high accuracy and ease of use. By randomly sampling both data points and features, multiple independent decision trees are constructed and predictions are obtained in parallel. Mathematically, the random forest algorithm is an additive model that makes predictions by combining a set of base models, where the final model is F and is the sum of individual Fi models. Each decision tree generates a prediction based on sample data and features. The final regression prediction is obtained by averaging the results from all trees. Here is the result of the effect of the tube voltage. This figure illustrates the effect of tube voltage on the operator's dose while keeping other parameters constant. The operator's dose is closely related to kVp. And as shown in this picture, when kVp was increased from 70 to 120, the dose increased by approximately 3.5 times. This is because increasing kVp raises the maximum energy of the X-ray beam, which not only enhances X-ray penetration but also increases the scatter radiation around the patient. Here is the result of the effect of changing beam quality. 6 different thicknesses of copper filtration were used. Figure A shows that the dose exhibits a sublinear increase as the thickness of copper filtration increased. This is because adding copper filtration leads to beam hardening, and with increasing kVp, the radiation dose to the operator becomes higher. At 70 kVp, adding a copper filtration may increase the dose by up to 4.3, and at 120 kVp, this factor only rises to 2.6 times. Here is the result of the effect of changing beam projection. The primary angle refers to the range from RAO to LAO, while the secondary angle refers to range of CAU to CRA. This figure shows the variation in operator dose under different primary beam projection angles and multiple beam energy levels. The operator's dose is significantly affected by the primary rotation angle such as LAO and RAO projection. However, within the range of 45 degree RAO to minus 30 degree LAO, the trend can be reasonably approximated using linear interpolation. For secondary projection angles, this figure shows that the dose trend remains relatively stable between 0 degree CRA to 30 degree. However, when the secondary angle exceeds CAU 15 degree, the dose decreases sharply. The lowest dose occurs at CAU 30 degree, while the highest dose is observed at CRA 15 degree. As shown in figure B, the dose can increase by up to 8-fold. In all cases, LA or CRA projections result in higher doses compared to RAO or CAU projections. This is because RAO or CAU projections allow the patient or the image intensifier to show the dosimeters. When the dosimeter is positioned at this specific location, the dose reaches its lowest point at 45 degree RAO. However, when the angle exceeds 45 degrees, the dose begins to rise again. Additionally, they analyze the effect of simultaneously changing both the primary and secondary angle on those under 70 kVp and 110 kVp. In the two figures above, the horizontal axis is represent the primary beam angle, It can be observed that when LL exceeds 30 degrees and is combined with CRA, the operator's dose increases significantly. Conversely, when LL is combined with CAU, the dose decreases, and the highest dose occurs at 75 degree RAO combined with 30 degrees CAU. 30 degrees CRA, while the lowest dose is observed at 30 degree RAO combined with 30 degrees CAU. This section compares three different field size, as shown in Figure A. The field size is directly proportional to the dose across different beam energy levels. This is because a larger size interacting with the patient generates more scattered radiation. Figure B shows that at higher kVp, the increase in dose is more significant than at lower kVp. Under the condition of a fixed field diameter of 20 centimeter, the impact of 70 and 120 kVp on those at different SID is compared. Increasing the SID reduces the beam projection area on the patient, causing a slight decrease in the scatter radiation ratio. Although scatter radiation decreases due to the increased distance, the scattered radiation is more likely to reach the dosimeter position, which may lead to a slight increase in the observed dose at that position. At lower kVp, increasing the SID has little impact on the operator's dose. However, at 120 kVp, the point scatter fraction decreases by 15%, while the dose ratio increases by approximately 20%. Table 1 summarizes the dose impact ratio for each parameter when changed independently. The study found that the primary beam angle and secondary beam angle have the greatest impact on the operator's dose, while SID has the least impact. As mentioned earlier, two regression models were used in this study. The first model is a polynomial regression model used to predict the ratio R under specific parameter combinations. The equation of the model is shown on the left, and the R value can be obtained by using the parameters in the table below. This model helps users assess the ratio R at a specific dosimeter position and is applicable to any X-ray beam setup with the scope of this study. The random forest regression model was used to evaluate the impact of various parameters on dose. Figure 14 demonstrates the accuracy of this model. The overall validation score R squared is 0.92, which indicates a very good result. Figure 15 shows that in the random forest regression model, primary and secondary beam projection has the most significant impact on dose, while the SID has a relatively smaller impact compared to other parameters. The discussion session analyzed the study results. The key finding is increasing the FOV from 20 centimeter to 30 centimeter increases the scatter ratio R by 2.5 times. For copper filtration, adding a 0.2 millimeter copper filter nearly doubles the scatter ratio R. For beam projections, LAO results in a higher radiation dose than RAO, and the CRA results a higher radiation dose than CAU. And they also has comparison with other studies. In the studies, however, the operator phantom was positioned near the patient's abdomen, which differs from the simulated position in this study. This difference in positioning led to significant variations in results, with operator dose differing by up to a factor of 10. And in this study, the operator position was set at here, which more accurately represents typical femoral or radial artery intervention scenarios. The future improvement is the simulation didn't include an operator phantom, which may have led to an underestimation of backscatter effects by approximately 10%. And in the future, the calculation of HP10 can be improved by introducing a correction factor. A summary is a study provides a detailed analysis of those impacts and proposes a predictive model, offering practical guidance for optimizing radiation protection in interventional radiology. Thanks for your listening. Anyone have questions? Thank you.
Can you identify or choose AA and RA effect to do this?
Although the study says they use RAF phantom, but they only simulate the dose here, which they usually put a dose meter location.
How does 2026 calculate the energy utilization?
The Eclipse tally estimates the energy deposition by integrating the track length photon and the weighting of it with the photon heat number, which represents the average kinetic energy.
I want to invest in page 14. Page 14. I want to ask what is the rating of R divided by A? And also I want to ask, is this result can be explained by the linear square law?
The R over A is the ratio of the scatter fraction R over the projected beam area on the KAP meter. And And the scatter fraction R decreases with increasing SID because the field area interacting with the patient and the KAP meter decreases. However, the R over A increases because while the scatter fraction decreases, the projected from beam area decreases faster. So this ratio increase.
Page 11. I want to ask why did the CAU and CRA is the dose war is larger at protein increase?
You mean CRA?
CRA and CA.
The CRA 15 degree is larger is because the operators is standing on the patient's right side, so it's more closer to the source.
Page 10. I want to ask what is the information of the factor is the result of
You mean figure B?
the factor
This factor is present the it present the 倍数，就是它 normalization，就是看它从就是没有用 filtration 到就是越来越厚的那个变化，然后这边指的是说，就是在70 kbp 的时候，它那个 filtration 的变化会影响的倍数比较大，就是跟 broader kbp 相比的话，就是倍数的数字。
Page 8. I want to ask what kind of data should grandmother tablets put at output?
You mean this equation? The y is the scatter fraction, and the x are the parameters that I mentioned. Yes.
Question. Page 11. Why does the angle of LAO have dose increase earlier than RAO?
Because in the LAO, the H ratio is closer to the operator, so it causes a higher dose.
Anyone have questions?
好，那今天2位同学是报告 paper 嘛，然后一位同学比较像是就是他自己研究实验的设计跟题目的报告。那我先就这个 paper 报告的部分哈，我还是建议同学就是说，像最后像书名这边他有提到一个 discussion part 哈，那当然这个 discussion part 我们就需要再多做一些延伸，就是不是只有 conclusion 嘛，因为这个 discussion part 就是说这一篇 paper 它的 limitation 在哪里，那它的没有回答到的问题在哪里，所以就如同第一位同学，他就说他之后想要延伸这个 ENCT 的这个 particle 在 breast cancer， 那你一定是看到说现有他们的这个 study 有什么样子还没有解决的问题，所以你要从这边再出发，你可能是要去改善这个，去改变这个 neo particle 的这个输送的途径，还是说你要用另外一个不一样的 model 还是说你要去 study 更多的 biodistribution 或者是 side effect 所以就是说我们在读那个 paper 的时候，其实 discussion 才是最重要的因为你要知道说这一篇 paper 它现有的这些东西是不是已经足够满足，还是说其实还有非常多需要在就是这些限制，然后他没有回答到的问题，那就同样就是你自己准备好了之后，同学就不用再问你说，那你为什么要选这篇 paper 嘛？因为你就知道说，因为我想要做的是什么，然后跟它的区别在哪里，这样所以就是提醒大家，就是如果之后你们是选paper 来报告的时候，就是你的那个 discussion 的那个 part 其实是最重要的一个部分嘛，因为别人做的你不太可能去 challenge 他，就是说他为什么要这样设计，因为你不知道他当时的他可能他的研究资源，他的这些实验的这些仪器设备的限制，可是他的 discussion 的这个部分才是最重要的。好，这是我们读 paper 的时候一个最重要需要去注意的地方。好，就是这样子提醒大家。好，那没有什么问题。好。